Today we are going to learn about mastering mask RCNN for instance segmentation. This tutorial will guide you through understanding the mask RCNN architecture, setting up the environment, training the model, and implementing it in real-world scenarios using Python and TensorFlow. Welcome to our comprehensive guide on mastering mask RCNN for instance segmentation. This video will delve into how mask RCNN elevates instance segmentation tasks, essential for precise object detection in dynamic environments. By the end of this session, you will be well equipped to implement mask RCNN using Python and TensorFlow. We will begin with an overview of the mask RCNN architecture, proceed with a comparison of other instance segmentation methods, and move on to setting up the environment for mask RCNN. You will receive a step-by-step guide to model training, learn how to handle edge cases and occlusions, understand performance evaluation metrics, explore real-world applications through case studies, and finally, adopt best practices for model optimization.
Mask RCNN is an extension of the faster RCNN model, designed to address the challenge of instance segmentation by efficiently detecting objects and generating a high-quality segmentation mask for each instance. The architecture consists of several key components. At its core, mask RCNN uses a backbone network, typically a ResNet or ResNet-XD, for effective feature extraction. Next, the Region Proposal Network, RPN, predicts regions of interest. Unlike the original RCNN, mask RCNN introduces an ROI Align layer, which solves the misalignment issue by precisely pooling features from the proposed regions. A crucial addition is the mask branch, a fully convolutional network that produces a binary mask for each region of interest, allowing for pixel-level segmentation. This integration of object detection and segmentation capabilities enables mask RCNN to excel in various applications, offering a more comprehensive understanding of the visual scene.
Instance segmentation is a crucial task in computer vision, distinguishing individual objects within an image rather than assigning a class label to each pixel as in semantic segmentation. Among the various methods available, mask RCNN stands out due to its robust integration of object detection and segmentation tasks. Compared to semantic segmentation, which does not differentiate between instances, mask RCNN provides a more granular approach by identifying each instance separately. When compared to faster RCNN, mask RCNN offers significant improvements through its mask head, which predicts segmentation masks alongside bounding boxes. This capability is particularly beneficial in scenarios involving overlapping objects, as it efficiently handles occlusions and precisely segments small objects. These advantages make mask RCNN the preferred choice for applications demanding high accuracy, such as autonomous vehicles and medical imaging.
Before diving into the implementation of mask RCNN, setting up your environment correctly is crucial. Start by installing Python, preferably version 3.7 or newer, and TensorFlow 2.x, which is compatible with mask RCNN. Use a virtual environment to manage dependencies efficiently without affecting other projects. Install essential libraries like NumPy, OpenCV, and Matplotlib, necessary for data manipulation and visualization. It's also important to download pre-trained weights, which speed up the training process and help achieve better results. Organize your project structure to include directories for datasets, models, and scripts. A well-configured environment ensures a smooth workflow as you proceed with model implementation and training. Training a mask RCNN model involves several critical steps. Begin by preparing your dataset, ensuring it is annotated correctly with bounding boxes and masks for each instance. Consider using data augmentation techniques, such as random cropping, flipping, and color adjustments, to enhance the model's robustness and generalization. Configure model parameters, including learning rate, batch size, and epochs, to optimize training. Utilize frameworks like TensorFlow's Keras API for a streamlined training process. As you train the model, monitor its progress through loss metrics and adjust parameters accordingly to prevent overfitting. Implementing these steps with precision will aid in developing a high-performing mask RCNN model tailored to your specific use case. In real-world scenarios, handling edge cases and occlusions is a common challenge in instance segmentation tasks. Mask RCNN is designed to address these issues effectively. Overlapping objects often confuse models, leading to inaccurate segmentation. To counter this, mask RCNN leverages multi-scale features, allowing it to capture detailed information at various levels of the image. Techniques such as non-maximum suppression help refine predictions, minimizing errors due to overlapping instances. For complex scenes, fine-tuning the model with custom data that represents specific challenges can significantly enhance its performance. By refining masks and improving accuracy, mask RCNN ensures reliable segmentation results even in dynamic and cluttered environments.
Evaluating the performance of a mask RCNN model is crucial to ensure its effectiveness in instance segmentation tasks. Key metrics include intersection over union, IOU, which measures the overlap between predicted and ground truth masks, providing a quantitative assessment of segmentation quality. Precision and recall are also important, indicating the model's ability to correctly identify and segment instances. One of the most comprehensive metrics is mean average precision, MAP, which evaluates the model across various IOU thresholds, offering a holistic view of its performance. Additionally, benchmarking the model against other state-of-the-art methods can provide valuable insights into its relative capabilities and areas for improvement. By employing these metrics, you can fine-tune the MaskR-CNN model to achieve optimal results. MaskR-CNN's robust capabilities make it suitable for a wide range of real-world applications. In medical imaging, it aids in precise diagnostics by segmenting organs and tumors, enhancing decision-making processes. Autonomous driving systems leverage MaskR-CNN for object detection and path planning, ensuring safety and efficiency. In the realm of surveillance and security, it enhances monitoring by accurately identifying objects and individuals in complex scenes. Agricultural monitoring benefits from MaskR-CNN by analyzing crop health and detecting pests, contributing to sustainable farming practices. Additionally, augmented reality applications use instance segmentation for interactive experiences, overlaying digital content onto real-world environments. These diverse applications highlight MaskR-CNN's versatility and impact across various industries. Optimizing a MaskR-CNN model involves several best practices to achieve superior performance. Hyperparameter tuning is vital, as it directly impacts the model's learning process. Experiment with different learning rates, batch sizes, and epochs to find the optimal configuration. Efficient use of computational resources, such as leveraging GPUs, can significantly speed up training and inference times. Regularization techniques, including dropout and weight decay, help prevent overfitting and improve generalization. Transfer learning strategies can be employed to leverage pre-trained models, reducing training time and enhancing accuracy. Lastly, continuous evaluation and refinement of the model based on performance metrics ensure sustained improvement and adaptability to new data. By implementing these practices, you can harness the full potential of MaskR-CNN for instance segmentation tasks.
In conclusion, mastering MaskR-CNN for instance segmentation opens up a plethora of possibilities in the field of computer vision. We have explored its architecture, setup procedures, and training methodologies, along with handling specific challenges like occlusions. The real-world applications and case studies illustrate its transformative impact across various industries. As you continue your journey in machine learning and computer vision, we encourage you to experiment with different datasets and scenarios, applying the concepts learned today. With practice and perseverance, you can unlock new insights and innovations using MaskR-CNN, contributing to advancements in technology and society.